So without further delay, I get to start today. So this is my group, and so we're the Scalable Autonomous Robotics Lab, and our lab consists of postdocs, PhD students, as well as MSc students. Those of you who are interested, we do actually have 2 openings for MSc students. Some of you might have seen the announcement by Tahir. So the work that we do, we are interested in sort of large-scale environmental monitoring using teams of robots. Most of the environments we focus on are environments that have very complex dynamics, like oceans and atmospheres, as well as these unstructured environments, as you'll see in one of our later projects. We think about how to coordinate highly heterogeneous sort of sensing assets, assets that have very different scales and resolutions potentially in their sensors, but also in terms of their mobility. And because these are very complex environments, deploying robots into these environments, there's all kinds of challenges. So we think about how do we do this? How do we monitor the environment, collect the most informative data that we can, subject to sort of significant resource limitations, like not having enough sensing resources all the time, subject to very severe communication constraints. And so a lot of the idea here is how do we make the most out of the data that we can collect and be able to build the best models and the most predictive models that will allow us to be used for improved planning and control of our vehicles in these environments. So some of the problems that we work on, so this is a distributed adaptive sampling problem. The idea here is you are deploying your robots out in the world. In this case, we have a big tank in our lab. We have our surface robots. They're collecting data on the dispersion of a dye, which is supposed to simulate something like an oil spill or a contaminant spill. And you're trying to figure out, right, how the contaminant or the chemical is being dispersed. And you want to be able to adapt the sampling locations of your vehicles to do this. Not sure if this is, and we can do this for pretty complex systems. This is a CFD simulation of a barium cloud breaking up sort of in an atmospheric setting. And so the idea here is how do you deploy a team of robots that has, cannot have full coverage of the space, but be able to collect good enough data that allows you to build good models of this environment that will then be used for planning mitigation purposes, okay? So something that you'll see if you come to Grass Weekend this weekend is our ability to so think about the environment and trying to understand what are the important dynamical systems features environments that our robots should be focusing on when we're thinking about collecting data. How do we do this estimation in an online fashion with our robots? And how this information can help us improve things like navigation, where you're really leveraging the environmental dynamics to do sort of energy efficient control and planning, okay? And a lot of these techniques can also be used to sort of understand the dynamics of traffic patterns, trying to figure out what are sort of regions where there's stagnation points in that flow, or points where you have very high throughput. We also think about, because we're interested in understanding the environmental dynamics, we do work in trying to think about using data to build computationally sort of efficient and models that can describe the dynamics of the environment. So in this particular example, we're interested in techniques that allows us to leverage sort of our understanding of the physics of the system, and with sort of acknowledging the fact that our understanding of the physics may not be complete or perfect. And so the idea here is to leverage the data, right, to sort of make up for our lack of understanding, okay? We have used this framework, and unfortunately, to sort of try and learn how to learn swarming dynamics and be able to design and extract single agent swarming controllers for teams. So another thing that we've done using a similar framework is trying to do to improve sort of models of systems with complex dynamics or quadrators. They're subject to highly nonlinear aerodynamic effects, especially when you're operating at very high speeds. And so how can you use these data-driven models to improve your ability to do controls, okay? We have worked, so this is an example of working in highly unstructured environments where the objective is to devise systems to be able to help scientists and experts, geologists, be able to be more efficient in their data collection out in the field. We have some work on sort of synthesizing and maintaining time-varying communication networks. And then last but not least, this is we have over the summer, we've been developing these autonomous boats. This is out on the Schuylkill River behind the Pennovation campus, okay? And so we are hoping to start a new set of projects focused on water quality monitoring and better understanding the impact of extreme weather on sort of the health of rivers. Okay, so I believe next person in line is Michelle Johnson's group, and who is it that hi. Let me make sure we have Francis and okay, hold on. Give me a sec. There we go. All good. That's the mic.
Good morning, everybody. My name is Francis. I am a first-year mechanical engineering PhD student. I'm here today to talk to you about the Rehabilitation Robotics Lab. We are a diverse group of people from multiple fields, including engineering and technology. And under Dr. Michelle Johnson, we are working to the goal of bridging the gap between engineering and rehabilitation. Our lab sort of functions on this dual principle of using accessibility and robotics to help people with non-traumatic brain injuries, including stroke, HIV, and cerebral palsy. We focus on these people with these non-traumatic brain injuries because a lot of time technologies and solutions aren't accessible to them. And it's because these people are in an unheard minority, and as a result, there aren't enough resources to assist them. And even the few resources that do exist are not often accessible due to reasons such as, money and location. Sorry. Now, to make sure the things we implement and we try are accessible, we work with a variety of organizations, including those in the community such as GRASP, Penn Medicine, and Children's Hospital of Pennsylvania, which is right down the street. But we also work with people internationally as well, such as the Cree Rehabilitation Center in Mexico and the Princess Marina Hospital in Botswana, again, to make sure that our solutions are accessible to people like outside the scope of what we see every day. Now, the first project I'm going to talk about today is the Rehab Cares project. And Rehab Cares is a community-based rehabilitation system. And it's because one of the biggest problems to accessibility is the fact that there often aren't enough therapists to help, different people. And so Rehab Cares is an all-in-one system with multiple subsystems for multiple therapy, sort of methods, allowing one therapist to see multiple people at the same time. Now, the star of the Rehab Care system is a TheraDrive, shown in the blue on the left and the white on the bottom. TheraDrive is a low-cost haptic arm for the purpose of therapy as well as assessment. The main group that TheraDrive focuses on is people with high motor impairment and high cognitive impairment. And from the graph, you can see those people have a lack of effective neuro rehabilitation strategies to help them out as well. And sort of the biggest group in this faction, we're looking at people with stroke and HIV. You might wonder why I say HIV. Well, as modern medicine advances, we're trying to see that people with HIV is trying to show these motor and cognitive impairments. And even now, people with HIV tend to suffer more from stroke and have worse recovery times. And to make sure this project is once again accessible, we are working closely together with clinicians in Botswana to make sure that it is, effective as a low-cost system. And we're hoping to use the TheraDrive as a framework for both assessment of people with upper extremity motor impairment as well as therapy. Sort of the next step for this TheraDrive project is the idea of haptic dyads. And haptic dyads is taking two of these haptic arms and using them at the same time with two different people. Now, one person would be more impaired and the other be less impaired. And the idea is that as they do activities together, the person who is less impaired can assist the person who is more impaired. This idea of less impaired helping more impaired is the same idea behind our biAdler. And biAdler is a bimanual, sort of arms to help people with upper extremity who have bilateral impairment, which means that one side of their body, at least one arm, is less impaired than the other. And so on the left, you have the black arm, on the right, you have the silver arm, and the black arm is the passive arm, and the silver arm is the active arm. So you put the idea is that the person with the impairment puts their sort of less impaired arm in the passive arm, and they move it around. The arm doesn't do anything except for collect data as they move it around. And the passive arm or the active arm reasons this data and uses it to sort of move the more impaired arm, allowing for therapy again, bimanually. Now, a lot of the solutions I presented to you so far are for adults, but babies or infants who have impairments as well are also an important group to pay attention to, and that's why we have the Panda Dream. And so the Panda Dream was developed to help diagnose CP and other neurodevelopmental disorders in babies. And that is because studies have shown that if you can sort of give therapy to children as they're younger, the younger they are, the better they are, because children have such high neuroplasticity that it leads to better or, a better quality of life later on. However, the problem with CP and other such impairments is that a lot of assessments only happen beyond the age of 1. And even when I say beyond the age of 1, it's a very, very small minority that can help children below, around the age of 1. And so, and another problem is the fact that these assessments require an extensive amount of time on the part of the parents to the babies, because it requires multiple sessions that take a very long time, as well as the fact that even the therapists or the clinicians require extensive training. So these aren't very often employed, and the Panda Gym is here to sort of bridge that gap using a machine to do most of the work. And the Panda Gym also is for infants who cannot yet crawl or walk. And so it sort of, again, aims to help people who are younger. And it has 3 major modes of sensing, which are cameras, the Panda toy, and a pressure mat. And so the cameras, as you can see here, we have a baby with, and we're using computer vision to track its or quantify its limb movements. And then the Panda toy, which is the panda-shaped toy, it's supposed to engage the infants. And as they play with it, we're capturing, as they grasp it, kick it, or even push it, we're capturing their instantaneous motions, and finally, we have the mat, which tracks their center of pressure. Now, these 3 things, center of pressure, spontaneous movement, and limb movement, are 3 important factors that have been shown to help diagnose, CP earlier on. And in the top right corner, we have our current version of the Panda arm. Don't worry, it's not a real baby. I'll explain what that is a little bit later. And so in the Panda Dream, we have 3 sub-projects, with the infant sentiment analysis, a soft sensor, and the infant simulator. The infant sentiment analysis uses, the infant sentiment captures, emotional data to make sure we get a kind of fuller extent of how their emotions affect their motion. The soft sensor uses fiber optics as well as 3D printed soft structures to make a more robust sensor, and as well the infosystem analysis allows us to collect control data so we can capture COP using computer vision, which is a novel thing that hasn't been tried. Finally, we have our Flow project. Our Flow is a telepresence robot to help people who don't have access to a therapist in person. And Flow uses a robot and not just a screen, because it's the socialness of it makes it more interactive for the users. And so it plays games with them, such as Simon Says, as well as it can display emotions. And currently Flow has been deployed in the community with over 50 interactions and 70 subjects. And Flow also uses computer vision to automate some of these processes. Sorry for taking up so much time, but feel free to contact us if you want to hear more questions. Thank you.
Hi, my name is Wei-Hsi Chen, and I'll be representing Khadlad, led by Daniel Kodischek. And so this is a portrait of our lab robots, and we do legged robots. Our lab's philosophy is to trying to understand the limitation of what a robot can do or cannot do. So we see here, there's like a squirrel doing the parkour motion. And we ask, can our robot do this? And we can't right now, but we want to understand why. So here are some focus that we're trying to understand. So the first is trying to understand the template and anchor of a system. We realize that animals are really just like a pogo stick. So we can understand them as a mass on a spring system. When they run, it's just doing a very simple dynamics. And these simple dynamics are easy to simulate and also easy to employ in different kinds of robots. So here we show two different kinds of bipedal robot, one without tail and one with tail. And they're using the same control strategy, but they move pretty well. The next, we're trying to see if we can implement the same simple dynamics in different kind of robot. So a pogo stick is kind of like a sagittal plane with only one legs. Can we implement it into a quadrupedal robot, like a robot with 4 legs? The answer is yes. And on the left, we have a Minotaur robot, and on the right, we have a Spirit robot. Again, they're using the same control strategy to mimic a bounding motion, and they did it quite well. So the next question we're trying to understand is the morphology of the robot, or the morphology of the animals. And we're trying to understand it with an embodied intelligence kind of perspective. The first question we wanted to ask is, what can the spine do? And implementing the spine on the robot, can it give us something that we can't do with traditional robots? So on the left, we have a paleontologist who is working on trying to bring the dead animal back to life, and doing some 3D printing and testing out the range of motion to try to test the hypotheses of what the spine can do. And on the right, we're trying to implement spine into a robot to have different kind of motions. And the next, we're trying to see if we can actually add some sort of compliance into a robot, because we believe that robots shouldn't be just rigid. And here we try to put origami as a compliant mechanism into the robot. And let's see. So here we can see that a robot can hop with just the origami structure. Okay, so we talked a lot about robots, but we also want to see if we can control the robots in an unknown environment. And it turns out that we can control the robot using navigation functions and sequential composition. And here we also had a lot of math model to show us that in order to do a reactive control, we must have a hybrid system. And we show that there is a global landscape that we can tune along to get a good reactive controller. So here Turner shows us that a robot can perform really awesome stuff like brachiating on the monkey bar and moving along different places and manipulating object at the same time. This is all just using transitional behavior to stitch two different steady state system together. So last but not least, we're trying to understand if our robots can help us do research better. And so we send our robot into the desert to help us collect data and also help the geoscientists to make better decisions. Okay, so this is our wonderful Khadlad members. And if you have any question or are interested in working with us, please contact our lab coordinator, Deidre. Thank you.
Hello, everyone. I'm Yiannis. I'm a postdoc working with George Pappas, and today I will give you a brief overview of the work that we have been doing in our group. This is a picture of a recent picture of our group. Essentially, our work is mostly motivated by autonomy applications that may range from environmental monitoring and mapping to even security and surveillance. And of course, there are several research challenges that we have to address when it comes to ensuring safe autonomy in the real world, and some of them are listed on this slide. And of course, this is more of a biased point of view based on our work. But in this talk, I will very briefly go through some of the four main research directions that we're pursuing in our lab that are focused on ensuring safety, resilience, and robustness for autonomous systems. Now, when it comes to safety, this is essentially the control architecture that we are advocating, that we are designing in our lab to ensure that mobile robots, autonomous systems, can navigate safely unknown environments. Now, this architecture consists of three main components. There is a perception system, which you can think of as a neural network that interacts with the real world. It takes us input images, and then it can generate some information about the geometric and semantic structure of the environment. Then this information is being fused over time within this mapping box. And then it can generate some probabilistic beliefs, or maps as we call them, of what we believe the environment looks like. And then this map is being fed into a planning and control layer that can generate paths and controllers for our robots so that some user-specified mission and safety requirements are satisfied. Now, we're actively working on designing those boxes. I will not go into those details, but I will only show you a video that demonstrates how this architecture works in a pseudo-real world. So in this video, the goal is to control a drone so that it can reach a person that is in this city while avoiding obstacles like this phone pole that you see there. And what is challenging there is that the environment is unknown. We don't know where this person is. We don't know where the obstacles, the poles are, and so on. So instead here, the robot is equipped with a camera and neural networks for object detection and classification. And then by using the previous control architecture, we can safely accomplish complex missions here. And we can also apply this architecture to multi-agent systems. This is a similar application where we want to control a swarm of 30 drones that have to navigate an unknown city to accomplish similar search and rescue missions. Now, apart from safety, we're also interested in designing distributed and resilient multi-robot systems. And one of the applications that we're interested in is on active sensing, active information acquisition. where here the high-level goal is that we want to control a team of robots so that we can accurately and efficiently track a phenomenon that's evolving in the environment. And typically, this kind of problems give rise to stochastic optimal control problems, where you have to maximize some information metric associated with the phenomenon that you want to track, subject to constraint related to your robot dynamics or the dynamics of the phenomenon. Okay, and we want also to design such controllers that are distributed, where each agent can make decisions locally and in an online fashion. And also we want to design resilient controllers that are robust to attacks that aim, for example, to disable our sensors. So this is just an experimental validation of our control architectures, where the goal is to control drones to track and localize ground robots that are moving randomly in the environment. Okay, another direction that we are pursuing in our lab is on robust deep learning. We all know that deep neural networks have enjoyed a wide range of successes, but at the same time, it has been shown that they are vulnerable to small input perturbations. And these perturbations can be adversarial. Also, they can be natural, for example, changes in the lighting conditions or in the background. So if we want to see such deep learning components in safety critical systems, we have to address this issue of robustness. And this is something we address in this project, where the goal is to design general training algorithms to enhance robustness of neural networks against such out of distribution natural changes. And the key idea here is that we need models for those natural changes, which can be either given to us or we can learn them using data. Also, we're doing work on evaluating robustness of neural networks. And we do that essentially here. We propose optimization frameworks to estimate Lipschitz constants of neural networks, which then we can translate to robustness certificates for our neural networks. And finally, so far we talked a lot about how we can design autonomy frameworks that rely on neural networks, either for vision or for planning and control. In this project, we follow a dual approach, where the goal is to verify such a closed loop system that has learning enabled components. And this mostly relies on employing reachability analysis tools to reason about safety. Okay, so this concludes the talk. If you have any questions, feel free to reach out to us. Thank you.
Okay, so Rahul, if you're ready, go ahead and share your screen. Rahul here.
Yeah.
Okay, perfect. So we're still waiting for your screen to show up on our end. There it is. Okay, whenever you're ready.
All right, I'm Rahul Mangharam. It's great to meet you all. I'm obviously speaking remotely. So I'm going to talk about what we do in my lab, focused on safe autonomous systems. And essentially, we design a lot of tools to get these autonomous systems to behave safely, either at design time or during their life cycle. In order to do this, we employ three different kind of tools where we use formal methods. We mathematically model these systems to capture the logic and the behavior of these systems so we can formally verify them. They obviously have actuation and control. And all of these systems that we work with are either safety critical or life critical systems. And the tools that we use have a lot of learning enabled components, because many times we cannot capture the dynamics or the behavior of the plants themselves with high reliability in white box models. But whatever research we do, we focus on the same type of question. We ask the same question: is how do we provide safety and performance guarantees for these closed loop life critical systems? And we apply them to implantable medical devices like pacemakers, defibrillators that are autonomous systems inside of your body that can shock your heart and that are out of your control and can cause life and death problems if there are bugs in the software. And energy systems. And today, obviously, I'll talk about just our autonomous systems over here. But we'll bring it to a fun level. because this is also about how can you get involved in the work that we do here in the lab. And so essentially, one of the fun projects we have is where we have 1/10 scale autonomous racing cars to basically explore perception, planning, control. And since it's 1/10 scale of a full-size car, you can actually race it down the corridors up to a max speed of 50 miles per hour, and it's fully autonomous. So it's 10 times the fun than a real autonomous car, because you can crash these, and you'll see we crash them a lot. But we have already built like an entire fleet of these cars. They're used in over 60 universities. And so we go from the mechanical aspects to putting all the sensors together, doing the sensor fusion, the entire perception, planning, control, autonomous vehicle stack is all ready, and it has been used in hundreds of these vehicles now. And that enables a lot of our research. So the vehicle is done, it's ready, and and we have many versions of this. And so I'm going to talk to you about our general theme of our research for 2021, 2022 is on learning multi-agent play strategies with improvisation. So when you have multiple agents, like say for example racing against each other where they're adversarial or they are collaborative, how do you manage this competition? How do you improve your odds? And we bring in model predictive control racing stacks. We look at overtaking and improvisations. How can you actually learn the behavior of your opponents and then outwit them? We look at behavioral cloning and many different aspects of perception, planning, control, all coming together. It's extremely hands-on too. So the first theme is really on looking at machine learning based dynamics modeling. So just starting with a few fixed parameters, how to design the fastest car. So you have a track and you're really trying to learn the dynamical model of the vehicle and then push it to its limit. So initially say the lap time is just 25 seconds, and now you're just going lap by lap by lap, and you're doing a learning based model predictive control. Say by lap 22, you have automatically started to tune the vehicle and it's down further to 20 seconds. And then by some other lap time, you can see the vehicle now is learning and it is also like drifting and is really pushing its limits. And anything, if it pushes it beyond this level, it will basically topple over or crash. And so then we look at like, what if the dynamics change and over time, and if there are failures in the model or if there are changes in the environment, and how does that affect this? A second theme is really on, really having rich and explainable perception and control. And this is essentially in racing, unlike just driving on the road, you have this tension between balancing safety. You want to be as safe as possible, but you can't just be too conservative because then you lose the race and then you're not going to be invited for the next race. No career over there, right? So how do you actually be safe enough, but be as aggressive as possible? And how do you deal with this tension? So we essentially use a self-play strategy to generate very competitive agents. And we are increasing our competence by finding a good diverse set of other types of agent and driving policies. But now say you've built up a pretty competitive agent that can now race competitively on its own and in the midst of other agents. So how does it actually, in just a few snapshots of observing the opponent, how can it identify with large levels or with very small levels of uncertainty, what is the driving policy and the behavior of the other agent, and how does it outwit them? How does it outrace them and come up with control and planning strategies to win along with any future opponent that is given? And so this work was part of ICML last year. And here you can see that this is, not just theoretical work on, optimization and control, but also working outside Levine Hall over here, right? So we like to see that our work actually does work on real platforms. A third theme is that, well, you could be given a track and you could be given a different car, but how do you build a reusable core autonomy? And where you have the same AV stack, and then based on different vehicles, different tracks, how do you actually optimize for that? And so we built a multi-domain optimization pipeline called TunerCar as part of ICRA 2022. And this automatically optimizes, what vehicle physical parameters you should tune, the planner, the controllers, so that you can get the fastest racing line and basically the most competent vehicle automatically. Right? So this is again happening right outside Wuhan. If you go outside now, you'll see this car. No, I'm just kidding. This happened a year ago. But that's Billy Zhang from our lab, Billy Zhang, and he is a former RoboMaster student on this project, right? So, and then we have this automatic pipeline of team 4 of how do you use previous designs to auto-complete new designs that you have. So if I have hundreds of previous drone designs and I have a new drone design to make, how can I use machine learning approaches to automatically do that, right? So a lot of our current work is on looking at how do we work with this tension of cooperation of multiple agents and adversary while we are racing. And that's what our current semester's efforts are focused on. F1 10th as a team has, we've been part of ICRA workshop and racing competitions, and that will happen in IROS 21. And there have been over 20 independent study RoboMasters projects in the last semester. So we really love working with RoboMaster students, PhD students. And all the former students have gone to really great places like Tesla, Autonomy, and so on. And we'd love that you be part of our lab. We're going to teach this course next semester, and we would love to have you in that course also. I'll stop over here. Thank you very much.
Thanks, Rahul. Get this. Yeah.
Oh, you're fine. Let's see, what's it doing?
There you go.
Do I have to share a screen from Zoom again?
Yeah, I have to share this one. Let's just make sure. That's good. There it is. Okay.
We can do that one.
There we go.
Get back to the beginning of it. Okay. Hi, folks. I'm Nick. I'm an assistant professor in ESE. Broadly speaking, my group works on trying to bring together ideas from learning and control to develop safe autonomous systems. I like starting my talk off with this video because it really highlights that it's a really exciting time to be working in this space, right? We've got really cool demos of things that I don't think any of us thought was going to happen even maybe just 10 years ago. But if we take a closer look, we see that as impressive as those demonstrations were, these things aren't really ready for prime time yet. A little bit of a bump and our Boston Dynamics robot's just going to crash and burn. We got Uber running a red. DeepMind advertises the thing in the middle as a positive. I don't view it that way. Anyways, the question becomes, how do we fix these things? And the broad approach that we take in our group is take ideas from dynamics and control things like models, guarantees, robustness, reliability, and try to combine them with the benefits of machine learning and big data, things like performance and adaptability and optimality. So we want to bring them together, and it's really at their intersection that we think that all of our nerdy hopes and dreams are going to come true. Broadly speaking, right now we have 3 research thrusts going on in the group. One of these is using data from good behavior. So let's say data from drivers or things like that to learn either certificates of stability or safe controllers. So I have some videos here of a compass gate walker and a self-driving car using our learned safe controllers to stay upright or on the road. Another question that we think about a lot in our group is perception-based control. What happens if the only way my system gets to see the world is through a complicated sensor like a camera? What's the right way to take into account the fact that there are errors and uncertainty that get introduced into this sensing pipeline? And then finally, what I'm going to use is kind of a catch-all for the rest of the work that we do. We look at the foundational theoretical questions related to control theory, machine learning, and especially how they interact together. And what I'd like to spend the next few minutes talking about is some of the work that we're doing in this last space, where we're really trying to build up a new foundational theory of machine learning and control. So I come from a robust control background, and arguably one of the most practically important contributions that robust control has made is identifying which kinds of systems are really easy to control and which systems are just impossibly hard to control, where it doesn't matter if you throw an optimal controller at it, your most sophisticated reinforcement learning algorithm at it, you're just going to be stuck with bad performance. And not only that, it can tell you why you're stuck with bad performance and how to fix it, to bring yourself to this space of easy control. So we've been trying to think about these same kinds of questions in the context of learning-enabled control, RL, and imitation learning. So one question we've been thinking about is what makes imitation learning easy? So for those of you who've played around with imitation learning in RL, you know that if you can, you want to use imitation learning. It's just easier, it's more sample efficient. For those of you who don't know what imitation learning is, just as a quick reminder, I have some system I want to control. There's some expert policy. It could be a human, it could be something computationally expensive that does what I want. And then I want to collect data using that expert policy and then use something like supervised learning or regression to learn my policy, to imitate it, to imitate the expert. Now, the challenge with imitation learning, which is that it's subject to something called distribution shift. And I'll just give you a little cartoon picture here to kind of illustrate why imitation learning can go wrong sometimes. So suppose this is the data that I collected to train my policy. And I'll use this cloud as kind of a picture to denote the distribution of these policies. I run my algorithm, I learn an approximate policy, and let's suppose I'm starting at this black dot and I want to try to run it. So the expert would follow this blue line, but because there's a little bit of an error in the learning step, I follow the red arrow. I end up here, we do this again, this is what the expert would do. I have a little bit of error and it actually kicks me outside of my training data. So now, while the expert would do this, the error that I incur is even larger. Now I'm really far outside of my training data. So whereas this is what the expert would do, my system just kind of goes haywire and blows up on me. So this is actually what happens with imitation learning and why it's not used very frequently. So one thing we want to understand is how much data do I need to actually make sure this doesn't happen? So all the nice properties of my expert are transferred over. And kind of the flip side of this is, how do the underlying properties of my expert determine whether something is easy or hard to learn via imitation learning? And so by combining ideas from nonlinear robust control theory and statistical learning theory, we're able to show that roughly speaking, the loss in performance, this deviation between my learned and expert policy, scales something like 1 over a stability measure of my system, and then 1 over the square root number of trajectories. So this tells me how much data I need to ensure good performance as a function of the underlying properties of my system. And so we can quantifiably explain now why easy tasks, so in this case, our easy task is a quadrupedal robot walking forward, can be learned easily with a little bit of data. Whereas if I try to do a hard task, here I'm trying to imitate an NPC expert that's walking in a circle, I need a lot more data. So here this fails pretty quickly. The thing to pay attention to is how long my robot goes before it gets reset. And this is work we've been doing with folks at Google Brain. Okay, the last thing that I want to wrap up with is we've been asking another question, which is what makes perception-based control hard? So my favorite demo system from robust control is the inverted pendulum. So if any of you want to do this demo after, we can do it. We have very nice theory that explains why this is easy to do. If I shorten it a bit, it gets harder. And if I make it really long, but I block my vision, it's impossible. So we can do this from robust control. And so what we asked was, what kinds of effects do these ideas have on reinforcement learning-based control when I'm using a perception map? And what we observed was a really nice correlation between what the theory predicts and what we see in terms of sample complexity. So we see that for the easiest or the less fragile system, the black curve, we get to our maximal reward really quickly. As we make the problem quantifiably harder and harder, we need more and more data. This is a toy example of telling you that if you have the wrong sensing, it doesn't matter what you do, you're going to be in trouble. And then last but not least, we've been trying to think about how to think about this a little bit more theoretically through the lens of adversarial learning. And while I won't go through the details, I'll just say that we're able to show that, again, as your system becomes harder from a robust control theoretic perspective, you end up with both increasingly worse performance overall, but a more dramatic trade-off between the robustness of, say, a learned Kalman filter or a learned perception map and the accuracy that it can achieve. So I'll just wrap up by acknowledging my awesome students and also some honorary members that we work closely with that aren't in the group, and then just leave up some relevant papers. If anybody has any questions or want to learn more, shoot me an email, drop by my office, always happy to talk. All right, thanks, folks.
Hi, everyone. I'm Lingzhi. Today, I'm going to representing Professor Jianbo Shi's group. So there are multiple aspects of computer vision tasks we're trying to work on. The first one I'm going to talk about is the first-person vision. So first-person vision is interesting in a sense that it's really the same source as what humans sees in our brain. But by understanding the human intention, this kind of first-person video, we really get the ability to put ourselves into someone else brain and trying to understand his intention. But to understand the first-person video, we first do some kind of structure from motion kind of techniques to reconstruct the the 3D scene of multiple people wearing the GoPro camera, and also recover the GoPro camera pose in the 3D space. Oh. Okay. So for some reason, I'm missing some slides here. In the past, we have studied like multiple aspects of first-person video. The first thing is to trying to basically infer the people's intention based on what he sees in the first person. So the first task we're trying to do is this trajectory retrieval from the physical connections, and the task formulation is that given the first-person video, we're trying to predict what's the future localization of this person and how he or she is going to move from the current state to the goal state. And we also study about how what people's attention from this first-person vision basically tell in this basketball scenario is gonna be if there are multiple players on the field, which person I'm going to pass the ball to. And another task we have also studied is generating the basketball players' behavior from a single image. And the form of this basketball player is in the form of 12D camera trajectory in this 3D field. And we're also trying to understand what deep neural network is trying, what kind of information this deep network is using to really understand human behavior from the first person. And from many of the tasks we have studied in this basketball scenario is that we understand, we see that deep neural network usually focus on the defender's body, on the different parts of the defender's body, and as well as the open space in the court. This is somewhat similar to what human system is trying to do when we're playing basketball. And the next thing we're trying to, next thing I'm going to talk about is the image synthesis part. We have also spent a lot of time trying to study how we can do image synthesis better, basically regenerating the visual world. So the first task we did many years ago is called image blending. So given a foreground objects with some not very precisely cropped mask and a background image, can we composite the image? Can we composite the foreground automatically into the background image such that it looks realistic? We take some inspiration from the points on image editing, which is a very old tool, and we make its original optimization problem into a differentiable iteratively solving optimization problems, and we can we were able to achieve this photorealistic image blending on the real image, as well as on the art painting. And we also studied the GAN-related kind of image synthesis. In this specific task, we're trying to do some more controllable image synthesis, conditional image synthesis. So on the left, we show that there's a conditional input image, which is basically a text description of what the birds look like. And all the bottom images are basically generated from this GAN network. But the different from the other works is that we're trying to do more controllable kind of representation in the generation process. such that we can sample the high-level features, basically changing the pose of this bird, or sampling the more middle-level features or low-level features, which more focus on the texture level information. We also study how image synthesis can be used for more general vision tasks like better recognition system. So this task, what we have done here is that given the image, the cityscape image, basically image that contains lots of pedestrian, cars, traffic light, this kind of objects, we just run the instance imitation or use the instance imitation labels on this image, and then we basically crop out all the objects into the scene, and then use another imaging painting network to fill in the holes in this background. And this process allows us to automatically generate lots of pseudo labels between the objects and the clean background, but we also know the pseudo ground truths where the objects were supposedly in the background scene. So by having this self-learning kind of framework, we're able to learn object placements and do lots of data augmentations. And we also have used similar framework in the affordance learning. And we have also done lots of research on high resolution imaging painting in collaboration with Adobe. So here we're going to quickly go over the current ongoing research. This research we're trying to do is to construct some kind of virtual escape room and have some human really play this virtual escape room and use the human data to boost the RL learning to basically improve the learning efficiency, that kind of things. And we have also working on neuron surgical projects where the goal is to run instance imitation on the fly to help the doctors to better recognize things on the fly. And our group has also provided lots of interesting improvements on the current instance imitation network, and also show quantitative improvements over their baselines. And we have also worked on this is also in collaboration with the company who is trying to do automatic accounting on the manufacturing. We also use we also design we also proposed some interesting techniques on top of the current instance imitation algorithms, and then trying to boost the performance. That's it. If you have any question or trying to work with us, please contact our group. Thank you.
So I think Robert, you're next.
Hi, everyone. I'm Robert Stuart-Smith, Director of the Autonomous Manufacturing Lab in the Weitzman School of Design, and an affiliate faculty member in GRASP. The lab extends a lot of research we've done into algorithmic design for building, design, and construction, into different means of behavior-based fabrication using robotics, in this case for precast concrete panels. And a lot of work has gone into design engineering approaches for additive manufacturing. This is a recent paper that was developing a multi-agent evolutionary approach to topological design. So multi-manifold structural columns in this case, looking at how basically a bottom-up swarm system behavior could be evolved to improve structural and geometric performance. So going from topological design, a lot of additive manufacturing for building construction uses continuous extrusion manufacturing methods, where there is gravitational material effects that impact both the structural integrity of a print, but also its aesthetic values. So we also design material placement in relation to structural and geometric properties through agent-based behaviors that are designed to be able to be done both offline and online programming situations. And in order to understand how to design with those, we also need to be able to visualize those and analyze those. So we developed the particle springs simulation model that models the material physics of the continuous extrusion and is able to produce visualizations like you see on the left. So in this case, it's a column that was printed upside down and the image is flipped, so it's inverted. And that software outputs basically a model that we can structurally analyze at high resolution, as well as a mesh that you can visualize. And this is something that industry just doesn't do, is deal with design at that resolution, at that scale. That work's been extended into larger scale building structures, where we understand that with the spacing of columns and walls in space, structural forces end up being anisotropic through building matter. And so we design anisotropic additively manufactured spaces. And we can do that through a multi-agent system that is adaptive to different structural loading conditions, where it takes in spatial, geometrical, and structural constraints in order to produce high resolution architectural designs. Now, while that's based on quantitative metrics that can be optimized through reinforcement learning and evolutionary solvers, we're also interested in how aesthetics can be played into that. Architects tend to struggle between efficiencies of material and other things and their aesthetic desires. And these things don't have to be in competition. So we're looking at a lot of computer vision methods, like you see here, GABA filtering, Power line work, Kenny contouring, and KD clustering, to start to break down the visual character and provide a quantitative metric for how buildings appear and how we can then incorporate that within optimization routines. We're also doing a lot of work on collective robotic construction. Recently, co-publishing a paper with Kirsten Pedersen, Niels Knapp, Daniela Roos, and Mikko Kovac, looking at a review paper of the field. This is some of the work we've done in the past. Looking at multi-agent systems, in this case for aero robot, construction of tensile structures, developing robust algorithms that the rules remain the same, but they're able to adapt to different environmental conditions to create different designs. This work's also extended in my London sister lab that I co-direct into an aerial additive manufacturing grant, together with Imperial College, University of Bath, and a bunch of construction companies and engineering companies. And our work in that is, once again, really into multi-agent swarm construction, where we're developing a software framework that deals with both real-time robot high-level planning control, as well as simulation modeling and its interface in design, and incorporating things like anticipatory structural analysis in the loop. So in this case, construction and design are inseparable. It borrows a lot from principles of stigmergic construction. A second project is looking at how we can apply the same types of principles to both off-site prefabricated manufacturing and on-site construction with a team of heterogeneous robots, where we use both fixed and mobile systems within one distributed system. It's a semi-autonomous system. We're incorporating external localization from motion capture and metrology for high precision work, but at the same time we decompose tasks in such a way that robots are able to adapt to what they've already built, to what each other has built, do real-time collision avoidance through onboard sensing, and basically perform things that often are considered offline programming, performed online in real time. And I think that's my last slide. One last project. This is a house we're building on campus. Both myself and Masoud Akhtarzadeh, who runs the PSL lab, who's also an affiliate faculty member in GRASP. It's really looking at a different form of manufacturing with robotics and how we can use that to produce a materially efficient small house, like a tiny house, with a super thin concrete construction, and how that can reduce waste, but also be able to be designed for disassembly, relocation, and reuse. So it's using robot hot wire cutting of EPS foam to create thin shell and also complex cavity precast concrete, substantially thinner than what you see in industry. And it also affords certain geometric freedoms, and a lot of the foam's used as insulation in the building. The interior of that building is also another research into fabric structures. So the interiors are kind of felt fabric. So we're developing computational models of that. Thank you.
Hello, how's everybody? Good. All right. I'm Cynthia Sung. I'm a member of the mechanical engineering department here, and our group does work in compliant and semi-rigid robotics. So to give you a sense of the kind of work that we do, I'm going to start with a video which many of you are probably very familiar with. This is me folding a paper crane. A lot of you have probably folded paper when you were young or just need something to fiddle with for your hands. If I unfold this sheet, then I get this crease pattern, which is basically an outline of the fabrication plan for this 3D shape. And what's interesting about this folding process is that first, the paper is a compliant material. It bends and it twists. And when I add folds into the structure, that adds hinges. So basically an origami pattern is a mechanism, right? It's a compliant mechanism. And in my group, what we're interested in finding out is how do we model, predict the behavior of, and then design the behavior of these sorts of compliant mechanisms. So one of the things that we're interested in my group is how can we tune the mechanics of a compliant structure or an origami pattern through its geometry. And there's an interesting theorem from computational geometry called the Bellows theorem. It states that if you have a closed structure and all of the faces stay the same size, then that structure is basically has invariant volume, which means that if you want to construct some sort of closed polyhedron, it's going to be theoretically rigid. And we can make use of that theorem in order to design compliant structures with tunable stiffness. So basically, the amount that the faces have to flex in order to change the volume of the structure gives us a measure of how stiff that structure is going to be. So I can take ideas like this. I can create bellows structures like the one you see here. This was actually a video from Wei-Hsi who presented earlier. And these structures are made out of very thin pieces of paper, but they are quite stiff. I can model these structures using spring networks. And this is a very common modeling technique for origami-inspired designs. And I can predict that if I change the geometry of these patterns, then I can get different types of mechanical responses. So here, what you're seeing in this plot is that by changing a single angle alpha by 1 degree, I can tune the structure to be very stiff. I can get buckling, I can get snap through. And I can use this type of idea in order to create a variety of different types of robots and functionalities. So in this design here, we made use of the fact that this bellows structure has some sort of snap through behavior in order to create a robot that can jump. All of the energy that is required for this robot to jump is stored inside of the pattern itself. And we can predict the amount of energy that's stored in the pattern and tune the amount of energy by, again, changing the geometry. I can also, as Wei-Hsi showed you earlier, use these same structures in order to make robots that can do continuous hopping. And these sorts of designs can also be used in a variety of other applications. So I can use these exact same ideas in order to model, in this case, a different pattern. This is what's called an origami magic ball. Again, I can predict what the force displacement response of this ball is. I can predict that it's going to change volume. I can add in some actuation mechanism. And then I can get a really interesting swimming robot that can change its volume and jet propel itself forward like a squid. So in this case, just like with the jumping robot, all of the energy required for the robot to expel a jet and push itself forward is provided by the skin, by the compliance in the pattern that we've designed. And by tuning the energy and stored inside of the skin, we can get the robot to be a more efficient swimmer or a less efficient swimmer, or we can change the symmetry or other types of qualities of the pattern in order to get to steer or do other tasks. In addition to these ideas, our lab is very interested in fabrication and how fabrication plays a role in the behavior of the the origami pattern. And in particular, we're interested in how we can get these patterns to assemble themselves. So one of the things that we do is investigate laminate-based fabrication processes that allow us to create these self-folding structures. So what you're seeing here is a very simple pattern that takes about 1 hour to put together. When you expose it to heat, it'll fold itself. And then since there's a magnet on this one, it can crawl away. More recently, we've been investigating models for how we can predict how this structure is going to self-fold. And because as the pattern becomes more and more complicated, the consistency of the self-folding process gets worse, right? And so right now we're looking at how we can design the fabrication plan in order to make sure that these robots self-fold consistently and reliably over many, many runs, so that potentially in the future, you could bring home a full envelope of these robotic sheets, dump them in your oven, and you get hundreds of robots at the end of the day. Again, all of these processes are supported by computation and models that we've been developing in the lab. And the last thing I'll bring up is that we're putting these into interactive user interfaces that we're hoping will make these design processes more accessible to the general public. So this here is what we call the Build-A-Bot software, which allows people to click and drag different parts together so that they can assemble a robot. The program helps the people to simulate the robot, figure out what it's going to do, update design parameters, and essentially test the robot in a virtual environment before it automatically spits out the fabrication plan so they can assemble the robot in about 30 minutes to an hour on their desk. And we're really interested in seeing how these types of software and design algorithms affect people's design experience and how they approach robot design. And so hopefully in the future, you'll be getting an email from us asking you all to help us with a user study where we're going to be investigating how people interact with this tool. So all of this work, of course, is done by the members of my lab. These are pictures of some of them, both human and non-human. If you're interested in meeting any of them, please feel free to reach out to them or drop by our lab on tomorrow at 1:30 to 4:30. Thank you. Last but definitely not least,
Hi, everyone. I'm Pikul. I am also in the Department of Mechanical Engineering, and I am an affiliate of RESP. So I'm just going to talk to you briefly about the work that we do in my lab. This kind of describes it overall. We're kind of a strange robotics lab. If you think about two main tools. One is electrochemistry, and the other one is software. So within my group, there's a whole section on energy storage, which is just looking at batteries. There's a section on multifunctional materials, and then there's a section on soft robotics domain. I'm just going to go through a couple examples of the work we do in my lab. This one is looking, this is an EFRI project that we have. This is in collaboration with Martin, Michael Posa, and then a few other people that are not at Penn. What we're trying to do is we're trying to make soft robots on floating surfaces. This is very useful, and because it can solve problems like moving patients in hospitals. One of our collaborators is a professor in nursing school, and moving patients around in hospitals is the #1 cause of injuries in nurses. It's the largest reason why it's like a cost unit here. And it also causes a lot of nurses to leave the profession. And so what we're trying to do is develop systems that can assist the movement of people, make it easier. We want to use, because it's online. Yeah, thank you. So we want to use, we're interested in doing this with soft materials. One, because there's a lot of natural compliance, so you have robustness to different types of people. Also possibly because it's safer and it's easier and more comfortable for the person you're moving around. The tricky part is it's hard to move soft materials around in a controlled way. We can do this in relatively static systems, or we can go from one state to another state in a relatively controlled way. And so there's been a lot of work on this, but doing this where you kind of go through a series of shapes in order to actually move someone in a controlled manner, and to be able to understand the forces that are imparted on these materials, as well as exert controlled forces so that you move them the way you want to move them. It can be quite difficult. And so that's what we're doing for this particular project. And we're doing this by combining different interesting materials like clutches into these membranes, understanding how to model these different membranes. We're developing sensing tools for soft material systems, and then also working with Michael Posa on the control of how do you interpret and manage the control of this, which can be very difficult because there's so many dimensions that you have to control. We also do the intersection of energy and soft robots, or just robots in general. In this particular case, we're really interested in energy because it tends to be a large limitation for a lot of practical uses of robots, both in the fact that mostly if you have a battery powered robot, you're usually spending at least half the time not operating because you're recharging. But also because if a lot of robots, especially if you get to smaller scale robots, you can only operate for minutes using the batteries that we have available today. So we're creating kind of multifunctional systems. This is an example of one where it's basically a synthetic, we call robot blood. This is a fluid, so it's water. It has certain ions in it. So those ions allow us to store energy using electrochemistry, just like your blood stores energy with glucose and oxygen. But also this allows us to pump this fluid around, which we can actuate soft robots with. And so this multifunctionality gives us a net 4x increase in the total energy of this system. And that's with pretty bad batteries. These batteries are about 3 times worse than current lithium-ion batteries. So we have a lot of kind of interesting work in this space of creating multifunctional materials to make robots better, both from the energy side, but also the sensing side and the actuation side. This is just one example that we've already published. But there's lots of domains here. We're also interested in incorporating sensing, neuromorphic sensing, and other types of ideas into these types of robotic systems. Here's another kind of example. You can kind of see a trend of energy, thinking about energy and robotics. This is an example where we created a robot that eats metal. So you can take this robot, you can put it on any, it's not really a robot, it's a vehicle. You can put it on any metal surface and it'll use that metal to power itself. You could also give it metal chips and it can eat metal chips in order to power itself. And what's cool too is it can do what we call electrochemotaxis. And so it can use gradients in the energy of atoms in its environment to control the way that it moves, which means you can control, you can make this move towards things without having any computer on board. So lots of cool dimensions like that. This is an example that's maybe not as interesting to this audience here, but here we're creating, I guess, self-healing metal, which might be useful for robots, for example, that are on Mars, where you can't really just replace the part. So this is the first example that I think anyone's ever demonstrated of repairing metal at room temperature. And so we did that very recently in our lab using electrochemistry. And we do other kind of ideas like this. So we're thinking about robotic systems, but also components of robots. How can we combine soft matter and electrochemistry together to make them last longer, be more functional, have more robustness, things like that. And this is, my lab is larger now, but this is an older picture pre-COVID of my lab. So please, if you're interested in this type of space, come let me know. And you feel free, like Cindy offered, to reach out to my students as well.
So let's give our speakers a final round of applause. Our graph overview. Those of you who are here, there is sort of takeaway food at the mezzanine level, so please help yourself. Thanks for those of you online. Thanks for